So, imagine wanting to understand everything around you, not just the big things, like mountains and oceans, but the tiny, tiny parts they are all made from. Imagine trying to keep track of all the different fundamental ingredients that mix together to become wood, or water, or the air you breathe, or the soft fur of a sleeping cat. It might seem like an impossibly huge task, like trying to count every grain of sand on a beach, or name every star scattered across the night sky. Where would you even begin? How could you possibly organize such a vast collection of different sorts of stuff? Well, wonderfully, cleverly, humans found a way. It's like discovering a secret map, not to buried treasure, but to the very essence of matter itself. Or perhaps, think of it like a grand family photograph, carefully arranged, showing all the relatives, every single basic type of material that exists, all gathered together in one place, showing how they relate to each other. This amazing guide, this comprehensive family album of the universe's building blocks, has a name. It's called the Periodic Table of Elements. And we can think of it tonight as a cozy chart of everything. It doesn't sound particularly cozy at first, perhaps. Periodic Table of Elements might sound a bit official, a bit scientific. And when you first see it, it looks like a grid, a colorful chart filled with little boxes, letters, and numbers. It might seem complicated, like instructions for something very technical. But let's put that feeling aside, just for now. Let's instead imagine it as something warm and familiar. Picture a large, beautifully organized pantry where every jar and container is perfectly labeled and placed, so you know exactly where to find the sugar, the flour, the spices, all the ingredients you need. The periodic table is like that, but for the ingredients of the entire cosmos. Each little box on this chart represents one basic ingredient, one element. An element is a substance that cannot be broken down into anything simpler by ordinary chemical means. It's like a primary color, red, yellow, or blue, which you can mix to make other colors, but you can't make red by mixing other colors together. Elements are the fundamental building blocks. Gold is an element. Oxygen, the air we breathe, is an element. Iron, strong and sturdy, is an element. The helium that makes balloons float is an element. And this chart, this periodic table, gathers every single known element, all the fundamental ingredients discovered so far, and arranges them in a very special, very meaningful order. It's not just a random list, it's a carefully constructed map. Think about a map of a country or a continent. It shows you where the mountains are, where the rivers flow, where the cities cluster. It shows you borders and connections. The periodic table does something similar for the elements. It arranges them in rows and columns, and where an element sits on this map tells you a lot about it. It tells you about its neighbors, the elements it sits beside. It tells you about its family, the elements it lines up with vertically. Just like on a geographical map, location matters. Elements in the same neighborhood on this chart tend to share similar characteristics. They behave in similar ways. Imagine one area of the map is full of elements that are shiny, solid at room temperature, and good at conducting heat and electricity. These are like the big, bustling cities of the elemental world, the metals. Think of iron, copper, silver, gold. They live together in a large region of the chart. Then, perhaps in another corner of the map, you find elements that are quite different. Maybe they are gases, invisible and light, like helium or the oxygen we mentioned. Or perhaps they are brittle solids or liquids that don't behave like metals at all. These elements live in different regions or neighborhoods on our chart, indicating their different natures. The chart groups them, showing us at a glance which elements are likely to be similar and which are likely to be quite distinct. Now, let's think about that other idea, the family photograph. Imagine a huge family reunion. You have grandparents, parents, aunts, uncles, cousins, siblings. In a big group photo, people often stand near their closest relatives. The periodic table is like that photo. The columns, the vertical lines of elements, are often called groups or families. Elements within the same family share certain traits. Much like siblings might share the same color, eyes, or hair, or a similar way of smiling. They might not be identical, but there's a family resemblance. They tend to react with other substances in similar ways. So, If you know something about one element in a family, you can make a good guess about how its siblings or cousins in the same column might behave. It's a wonderful way to see the connections, the relationships between these fundamental ingredients. And the rows, the horizontal lines across the table, you could think of these like different generations in the family photo, or perhaps like different streets in our elemental city map. As you move across a row, the properties of the elements change, gradually, predictably. It's like walking down a street where the houses slowly change style, or watching family members grow and change through different stages of life. Each row represents a different level of complexity, a different energy level in a way we can explore more later. But for now, just know that moving across a row signifies a steady, progressive change in character. So, this chart isn't just a list, it's a system. It's an incredibly elegant way of organizing knowledge. Every element has its own designated spot, its own little square home on the chart. Inside each square, you'll usually find a 1 or 2 letter symbol, like a shorthand name for the element, like O for oxygen or Fe for iron, which comes from its Latin name, ferrum. There's also usually a name written out, and importantly, a number. This number, called the atomic number, is unique to each element. It's like a specific house number that tells you exactly which element lives there. The elements are arranged on the table primarily in order of this atomic number, starting from 1, hydrogen, the lightest and simplest, and going up, one by one, across the rows and down the columns. This numbering system provides a fundamental order, ensuring every element has its precise place. It's quite something to think about, isn't it? That everything you can touch, see, or even imagine being built, the chair you might be sitting on, the water in a glass, the distant stars twinkling in the night sky, your own body. Everything is made from combinations of the elements listed on this single chart. Just about 100 or so fundamental ingredients give rise to the infinite variety of the universe. It's like having a relatively small alphabet that can be used to write every story, every poem, every book imaginable. The periodic table is the alphabet of matter. And seeing it all laid out, organized so beautifully, can feel quite comforting. It takes the seemingly chaotic world of substances and reveals an underlying pattern, a hidden logic. It's like finding the key to a code or understanding the rules of a game. It makes the world feel a little less random, a little more understandable. That's why we can call it a cozy chart. It brings everything together, all the fundamental bits of reality, into one comprehensible picture. It's a human achievement, born from centuries of curiosity, experimentation, and careful observation, this ability to map the very fabric of existence. Don't worry if it still seems like a lot to take in. Like any detailed map or large family photo, you don't need to understand every single detail at once. We can explore it gently, piece by piece. We can visit different neighborhoods on the map, meet different elemental families, and get to know their personalities. We can learn why certain elements live where they do, and what makes them special. For now, just hold the image in your mind. A grid, a chart, a map, a family gathering. A place where every basic ingredient of our world has a home, a name, and relationships with its neighbors. It's our guide to the building blocks of everything, waiting patiently to share its secrets. It's the periodic table, our cozy chart of everything, a testament to the underlying order and elegance woven into the very structure of the universe. And as we drift towards sleep, we can feel a sense of quiet wonder at this map, this family portrait that contains, in its neat rows and columns, the recipe for reality itself. It promises that even the most complex things have a fundamental simplicity, an organized beginning, waiting to be understood. So, let us think then about this grand recipe book, this detailed map, this warm family gathering held within the frame of the periodic table. If it holds the secrets to the recipe for reality, what are the actual ingredients listed on its pages? If it maps the very fabric of existence, what are the fundamental lands and territories it describes? And if it's a family portrait, who are these individuals? These faces looking out at us from their neat rows and columns? These fundamental things, the ones that have their own special place marked on the chart, are called the elements. It's a simple word, perhaps one you've heard before, but it holds within it a universe of meaning. Think of them as the world's tiniest, most essential bricks. Imagine, if you will, a vast cosmic playroom, filled not with colorful plastic blocks, but with something far more fundamental, something gifted by the universe itself. These are the elemental bricks. They are not bricks made of anything simpler, the way a house brick is made of clay. No, these elemental bricks are the clay, the ultimate substance, the starting point. You cannot take one of these elemental bricks, say, a brick of pure, shining gold, or a brick of invisible, lighter-than-air helium, and break it down into different kinds of substance bricks using ordinary means. A gold brick is just gold, through and through. A helium brick is just helium. They are pure. They are fundamental. They are the simplest forms of distinct matter that exist, the irreducible ingredients provided by the cosmos. Picture these tiny, potent bricks. There aren't countless, infinite types. That's part of the magic, part of the comfort. Remember the cozy chart? It organizes them all, and there are only about 118 known types of these elemental bricks that make up everything we have ever encountered, from the farthest star to the dust beneath our feet. Just over 100 fundamental building blocks. Some of these bricks are very common, like the sturdy, reliable bricks of carbon, the essential framework of all life as we know it. Or the bricks of oxygen, the invisible airy bricks we breathe, vital and energetic. Then there are the light, simple bricks of hydrogen, the most abundant brick in the entire universe, found in the stars and in every drop of water. There are metallic bricks, like strong, grey iron, forming the core of our planet and the structures around us, or conductive copper, carrying electricity silently through wires. There are bricks of silicon, making up sand and glass and computer chips. Imagine these bricks, each type with its own unique feel, its own weight, its own character, its own color, though many are silvery metals or colorless gases. Some are heavy and dense, some are light as a feather. Some are solid and strong, some are liquids that flow like mercury, some are gases that drift unseen. Some are friendly and love to join together with other bricks, while others are aloof and prefer to remain alone. These are the elements. These are the names you see in the little boxes on the periodic table. Hydrogen, H, helium, He, carbon, C, oxygen, O, nitrogen, N, iron, Fe, gold, Au, silicon, Si, each one a unique type of foundational brick. Now, look around you, even in the quiet darkness of your room. Everything, absolutely everything, is built from these elemental bricks, cleverly stacked and joined together in countless combinations. The wood of your bed frame, it's mostly carbon bricks, joined with hydrogen and oxygen bricks, arranged in long, complex chains. The soft cotton sheets, again, carbon, hydrogen, and oxygen bricks, woven into fibers. The air you are breathing in, right now, it's a gentle mixture, mostly nitrogen bricks and oxygen bricks, drifting freely around you. Think of the water you might drink, cool and clear. It seems like one simple thing, water. But it's actually a combination, a partnership between two types of elemental bricks, two lightweight hydrogen bricks bonded tightly to one energetic oxygen brick. That specific combination, H2O, always makes water, just as stacking toy bricks in a certain way always makes a particular shape. Change the combination, change the substance. The glass in the window pane, letting in the moonlight, it's primarily made of silicon bricks and oxygen bricks, locked together in a strong, transparent structure. The metal legs of a chair, or the handle on a door. Likely iron bricks, perhaps mixed with a few carbon bricks to make steel, or maybe shiny aluminium bricks, or warm-toned copper bricks. Even you, yes, even your own body, lying here peacefully, is a masterpiece built from these elemental bricks. You are mostly oxygen bricks by weight, because of all the water in you, followed closely by carbon bricks, the backbone of your organic molecules, hydrogen bricks, partnered with both oxygen and carbon, and nitrogen bricks, essential for proteins. Then there are smaller but vital amounts of other bricks, calcium bricks for your bones and teeth, phosphorus bricks for energy transfer, potassium and sodium bricks for your nerves to send signals, a tiny bit of iron bricks at the heart of your red blood cells carrying oxygen. You are a walking, breathing, thinking structure assembled from the universe's fundamental building blocks. It's a rather wonderful thought, isn't it? That the staggering complexity of the world, the endless variety of substances, hard rocks, soft fur, flowing rivers, invisible gases, living plants, distant stars, and thinking beings are all constructed from a limited set of basic ingredients. It's like having a cosmic alphabet. Just as we use only 26 letters to write every word, every poem, every story imaginable, the universe uses its 100-odd elemental letters to write the entire story of matter. Think of it perhaps as a cosmic kitchen. The elements are the fundamental ingredients stocked in the pantry: hydrogen flour, oxygen water, carbon sugar, iron filings, nitrogen gas, silicon sand, gold dust. From these basic staples, the universe cooks up everything else. Water is a simple recipe: 2 parts hydrogen, 1 part oxygen. Air is a mixture, mostly nitrogen, some oxygen, a pinch of others. Rocks are complex mineral cakes baked from silicon, oxygen, aluminium, iron, calcium, and more. Living things are incredibly intricate molecular feasts, orchestrated primarily around carbon, hydrogen, oxygen, and nitrogen. The key is that these elements are where the buck stops, chemically speaking. You can take a complex substance, like wood, and break it down. You can burn it, releasing carbon dioxide, carbon bricks, yawon, oxygen bricks, and water, hydrogen bricks, yawon, oxygen bricks, leaving behind ash, various mineral bricks. You can take salt, sodium chloride, and use electricity to split it into shiny sodium metal bricks and pungent chlorine gas bricks. But you cannot take a pure sodium brick and, through any ordinary chemical reaction, turn it into something simpler. It remains sodium. You cannot take a pure carbon brick and chemically decompose it into anything other than carbon. They are elemental. They are the foundations. This is why the periodic table feels so comforting. It's not just a random list, it's an ordered presentation of these fundamental building blocks. It tells us, here they are, these are the basic bits. Everything else is just combinations of these. It reveals a profound simplicity underlying the apparent chaos. The universe, for all its vastness and complexity, is built upon principles we can grasp, starting with these elemental bricks. Each brick type, each element, has its own personality, its own way of behaving and interacting. Some, like helium and neon, are like perfectly smooth, self-contained spheres that rarely connect with others, the noble gases residing quietly on the far right of the table. Others, like sodium and potassium on the far left, are incredibly reactive, eager to bond with almost anything they meet. Carbon, in the middle, is a master connector, able to form long chains and complex rings, the basis for life's intricate structures. The table organizes them by these very properties, grouping similar personalities together in columns, arranging them by increasing complexity across rows. So, as you rest, imagine these elemental bricks, not as cold, hard facts, but as the quiet, underlying truth of the material world. Picture the gentle oxygen bricks mingling with nitrogen bricks in the air around you. Feel the presence of the carbon, hydrogen, and oxygen bricks that form the structure of your own resting body. Think of the water molecule, a tiny trinity of hydrogen and oxygen bricks flowing through you, through the earth, falling as rain. Consider the solid earth beneath, a vast assembly of silicon, oxygen, iron, aluminium, and countless other elemental bricks, packed tightly together. See the distant stars, fiery furnaces forging heavier bricks from lighter ones, powered primarily by the simplest brick of all, hydrogen. Everything connected, everything stemming from these fundamental origins. The universe isn't just a random jumble, it's a construction project of magnificent scale and intricacy, using a surprisingly limited set of exquisitely designed building blocks. These are the elements, the world's tiniest, most significant bricks. And knowing they exist, knowing they are organized, knowing they are the basis of all things, can bring a sense of peace, a sense of quiet wonder. The complexity we see is built upon a foundation of simplicity, an elegance woven into the very fabric of being. And the periodic table is our guide, our map, our key to understanding these essential, elemental truths. Allow your mind to drift now, picturing these fundamental particles, the silent, invisible architects of everything, resting, just like you, until a new day calls for new combinations, new structures, new wonders built from the same timeless, elemental bricks. Let your awareness settle, drifting down from the grand structures of the universe, past the mountains and oceans, past the very air you breathe, past even the idea of those fundamental elemental bricks we spoke of. Settle further still, allowing your focus to soften and narrow until you are contemplating just one single, solitary brick. Perhaps it's a brick of the oxygen you inhale, or a brick of the carbon within you. What is this single, ultimate piece? What lies at the very heart of an element, the smallest possible fragment that still holds the essence of, say, gold, or iron, or helium? This tiniest conceivable piece, the true building block, carries a gentle name, the atom. Say it softly to yourself, atom. It comes from an ancient word meaning uncuttable, for it was once thought to be the final, indivisible limit of matter. While we now know we can look even deeper, the atom remains the fundamental unit of an element. A single atom of gold is gold in its purest, most essential form. A single atom of hydrogen is hydrogen. It's like a single grain of finest sand, still embodying the beach, or one perfect, tiny droplet holding the nature of the ocean. This is the atom, the elemental self. Imagine now drawing closer to one such atom. Let it be an atom of oxygen, perhaps part of the air filling your lungs. As you approach, you find it isn't a solid, uniform speck like a miniature brick might suggest. Instead, it possesses an internal structure, a delicate and intricate architecture, humming with a quiet inner life. At its very core, like a seed holding the potential of a great tree, rests the heart of the atom, the nucleus. Picture this nucleus not as something hard or sharp, but as a dense, quiet presence. It's the anchor, the gravitational center of this minuscule world. Within this core, nestled closely together, like smooth, heavy pebbles warmed by an inner sun, reside two kinds of particles. One type carries a gentle, positive nature, a subtle pulse of energy. These are the protons. Feel their quiet, unwavering positivity, a defining glow at the atom's center. The number of these protons is profoundly important. It's like the atom's unique fingerprint, its secret name. It is the precise count of these protons that declares, "I am oxygen," or "I am carbon," or "I am helium." An atom with 8 protons is always oxygen, wherever it might be found in the universe. An atom with just 1 proton is always hydrogen, the simplest element of all. This positive charge, this proton count, is the element's unchanging identity card. Alongside these protons, sharing the space within that central nucleus, are their companions, the neutrons. Imagine them as calm, steady presences, lacking that positive pulse but possessing a similar weight, a similar substance. They are the quiet guardians, nestled among the protons, adding stability and mass to the core. They don't define what element the atom is, that's the proton's role, but they contribute to its overall balance and heft, like silent partners ensuring the nucleus holds together peacefully. Together, protons and neutrons form this dense, central point, the atom's quiet, unwavering heart. Now, allow your awareness to drift outwards from this calm, dense center. You might expect the rest of the atom to be packed tightly around it, but instead, you encounter space. A surprising amount of open space, vast and airy relative to the tiny nucleus. It's as if the nucleus, that cluster of protons and neutrons, were a single speck of dust suspended in the middle of a grand empty cathedral. The atom is mostly emptiness, a realm of potential rather than solid stuff. But this space is not truly empty. Far out from the nucleus, moving within this vastness, are the other crucial residents of the atom, the electrons. These are incredibly tiny, almost weightless compared to the protons and neutrons in the core. And they are in constant motion, not randomly, but in pathways, in orbits, like minuscule planets journeying around their central sun. Picture them not as frantic, buzzing insects, but perhaps as tiny, shimmering motes of light, tracing elegant, predictable paths through the atomic space. They move with incredible speed, yet their journey seems less like a race and more like a dance, a continuous, graceful weaving of patterns around the distant nucleus. These electrons carry a negative charge, a perfect counterbalance to the positive charge of the protons nestled in the core. In a balanced, neutral atom, the number of these orbiting electrons exactly matches the number of protons in the nucleus. So, our oxygen atom, with its 8 positive protons, is typically embraced by 8 negative electrons. Their opposite charges attract a gentle but persistent pull that holds the electrons in their orbits, preventing them from flying off into the void. It's this balance, this dialogue between the positive core and the negative electrons, that gives the atom its overall neutrality, its completeness. Think of the electrons not just scattered randomly, but occupying specific regions, specific energy levels or shells, like nested spheres of mist surrounding the nucleus at different distances. The electrons in the innermost shell are held most tightly, closest to the positive pull of the core. Those in the outer shells are further away, experiencing a gentler attraction, defining the atom's edge, its boundary with the outside world. It's these outermost electrons, the valence electrons, that are most involved when atoms meet and interact, when they link together to form the molecules that build everything around us. Their dance determines how the elemental bricks connect. So, the analogy of a tiny solar system is a gentle starting point, a central, heavy sun, the nucleus, with much lighter planets, the electrons, orbiting in the vast space around it. But perhaps it's even more delicate than that. Imagine the nucleus as the still point, the quiet center, and the electrons as shimmering clouds of probability, zones where these tiny dancers are most likely to be found, weaving their energetic patterns. The structure is defined more by energy and balance than by solid objects following fixed tracks. Consider again the scale. If the nucleus were a marble placed in the center of a huge sports stadium, the electrons would be like grains of sand whirling around the outermost seats. Most of what constitutes the atom, the space it occupies, is this empty region through which the electrons trace their paths. It's this spaciousness, this internal architecture, that allows atoms to interact, to bond, to compress, and to form the diverse materials we see and touch. The solidity we perceive in a table or a stone is less about densely packed spheres and more about the interactions of these electron clouds, the forces operating within this atomic spaciousness. And remember, the identity of the element is forged in that tiny, central nucleus. One proton, one electron dancing around it, the light, simple hydrogen atom, the fuel of stars. 2 protons, 2 neutrons, 2 electrons in their orbital dance, the stable, inert helium atom filling birthday balloons. 6 protons, typically 6 neutrons, 6 electrons arranged in their shells, the versatile carbon atom, the backbone of life itself. 8 protons, usually 8 neutrons, 8 electrons, the vital oxygen atom, essential for breath. Each number, each unique configuration of protons defining the core and electrons defining the periphery, creates a distinct elemental personality, a different kind of brick with its own unique properties and ways of connecting. This hidden world within the atom, this realm of protons, neutrons, and electrons, is a place of profound order and balance. It's a microcosm governed by fundamental forces, operating with a quiet elegance. The seemingly chaotic dance of electrons follows precise rules of energy and position. The nucleus holds together through powerful, short-range forces. Everything is in relationship, a dynamic equilibrium that persists across eons. So, as you continue to rest, picture this intricate world repeating endlessly, billions upon billions of times, within every substance around you and within you. See the quiet hum of the nucleus, the positive glow of the protons, the steady presence of the neutrons. Sense the vast space within each atom and the graceful, energetic dance of the electrons in their distant orbits. like whispers of light defining the atom's reach. Know that the elemental bricks themselves are not just simple blocks, but miniature universes, each with its own internal structure, its own specific count of these fundamental particles determining its nature. The simplicity we spoke of earlier, the limited set of elemental bricks, gives way to this deeper layer of complexity, yet it too is built on simple rules. The number of protons defines the element. The dance of electrons defines its interactions. It is a world of quiet wonder, this inner space of the atom, the foundation upon which all material reality is constructed, resting peacefully, just as you are, within the stillness of the night. Now, imagine all these different kinds of atoms, these elemental bricks, each defined by its unique count of protons, like a large and growing family. There's the atom with just one proton, simple and light. Then the one with 2 protons, still light but different. The one with 3, 4, 5, and so on, each number bringing forth a distinct personality, a unique way of being in the world. As people began to understand this family, this diverse collection of fundamental building blocks, they naturally wanted to give them names, just as we give names to people, pets, or even special places we love. Giving names helps us talk about things, to share our understanding. And so, the elements received their names that often hinted at their properties, or where they were found, or even honored the scientists who discovered them, or the myths of long ago. We have hydrogen, the water former; helium, named for the sun, Helios, where it was first detected; lithium, from lithos, the Greek word for stone; oxygen, the acid former; carbon, the element of coal, of carbo. Each name holds a little story, a whisper of its identity. But think about when you have many friends, or when you're writing notes, or trying to share ideas quickly. Sometimes, full names can feel a little long, a little formal for everyday use. You might call your friend Alexandra Alex, or Benjamin Ben. You might use initials for places you visit often. It's a way of making things simpler, more familiar, easier to handle. Scientists, as they explored this ever-expanding family of elements, felt the same need. They needed a quick, easy way to refer to each element, a shorthand that everyone could understand, no matter what language they spoke. And so they came up with a beautiful, simple system, a set of secret codes, or perhaps more accurately, gentle nicknames for each element. These aren't complicated codes meant to hide things, but rather simple labels, like little initials embroidered quietly onto each element's identity. Usually, it's just 1 or 2 letters, taken from the element's name, a quiet abbreviation, instantly recognizable once you know the key. Think of hydrogen, the very first element, the lightest one, with its single, solitary proton and that one electron dancing far out. Its nickname is simply H, just H. A single, straightforward letter for the simplest element. Picture that H, floating gently, representing that fundamental building block. When a scientist writes H, others know instantly they mean hydrogen, the element that joins with oxygen to give us water, the element that fuels the stars. It's like seeing the initial J and knowing it refers to your friend John. Simple, clear, and understood. H for hydrogen, resting lightly, peacefully. Then comes helium, the second element, with its 2 protons nestled in the nucleus. It's also a very light gas, the kind that makes balloons float high up into the sky, silent and graceful. Now, they couldn't just use her again, because that nickname was already taken by hydrogen. It would be like having 2 friends named Henry in the same class. You'd need a way to tell them apart. So, helium was given a 2-letter nickname, he, the first 2 letters of its name, he. You can almost feel the soft breath in that sound, like a gentle lift. When scientists see he, they know it's helium, noble and aloof, rarely joining with other elements, content in its own completeness, like a quiet observer drifting peacefully. Moving along the family line, we find lithium, the element with 3 protons. It's a metal, but surprisingly light, soft enough to cut easily. It's also quite eager to interact with other elements. Its nickname follows the pattern Li, the first 2 letters, Li, a short, quick symbol for this reactive light metal. It's like a little spark, that Li, hinting at the energy held within. Think about the air you are breathing so softly, so steadily. A vital part of that air is oxygen, the element with 8 protons. Oxygen is essential for life as we know it, involved in breathing, in burning, in rusting. Its nickname is beautifully simple. O. Just the letter O. Round and open, like a breath taken in and released. O for oxygen. It feels fundamental, essential, just like the element itself. When you see that O, you can almost sense the life-giving presence of oxygen, quietly supporting the world around you. And what about carbon, the element that forms the backbone of life itself? With its 6 protons, carbon is incredibly versatile, forming chains and rings, building the complex molecules found in plants, animals, and you. Its nickname is C. Just C. Strong, simple, central, C for carbon. It stands like a fundamental pillar, the basis for so much structure and complexity in the material world, yet represented by this single, unassuming letter. So you see the pattern. Often the first letter, like H for hydrogen, O for oxygen, C for carbon, and if that letter is already used, the first 2 letters are often chosen, like He for helium, or Li for lithium, or perhaps Ne for neon, the element that glows red in signs, or C for silicon, the element found in sand and computer chips. These little letter codes are like quiet acknowledgements, simple ways to point to each specific element with its unique number of protons and its characteristic dance of electrons. Now, sometimes, the nicknames seem a little surprising, like meeting someone named Robert, who everyone calls Bob. The nickname doesn't seem to come directly from the common name we use today. This often happens because the element was known long ago, perhaps in ancient Rome or Greece, or by alchemists in the Middle Ages, and it had a different name then, often in Latin. The nickname we use today might come from that older, almost forgotten name. It's like a little echo from the past, a connection to the long history of discovering and understanding these fundamental substances. Consider sodium. It's a soft, silvery metal, very reactive, and part of common table salt, sodium chloride. Its nickname isn't S, that's used for sulfur, or So. Its nickname is Na, N-A. This comes from its Latin name, natrium. So, Na is like a secret handshake, a nod to its ancient name, known across the world by scientists who understand this quiet code. Na for sodium, a little unexpected, but holding its own history. Similarly, think of potassium, another reactive metal, important for our nerves and muscles, found abundantly in bananas and potatoes. Its common name starts with P, but P is the nickname for phosphorus. Potassium's symbol is K, just K. This comes from its Latin name, kalium, which itself might have come from the Arabic word al-kaliya, meaning plant ashes, where potassium compounds were first isolated. So, K for potassium, another echo from the past, a single letter carrying centuries of discovery. What about iron? The strong, familiar metal used to build bridges and tools, the element at the core of our planet and vital in our blood. Its nickname isn't I, that's iodine, or Ia, that's iridium. Its symbol is Fe, Fe. This comes from the Latin word for iron, ferrum. Fe, it feels strong and dependable, just like iron itself. A 2-letter code linking the modern understanding of this element back to the Roman blacksmiths and warriors who relied upon its strength. Fe for iron, solid and enduring. And then there are the precious metals, known and valued since antiquity. Gold, glowing, heavy, resistant to tarnish, fashioned into jewelry and treasures. Its name starts with G, but its symbol is Au, A-U. This beautiful symbol comes from its Latin name, aurum, which means shining dawn, Au. You can almost see the soft gleam of gold in those letters, a symbol as precious as the element itself, whispering of sunrise and timeless value. Au for gold, luminous and rare. Silver too, cool and reflective, the best conductor of electricity. Its symbol isn't S or C, it's Ag, Ag, from the Latin argentum, Ag. It feels sleek and bright, like moonlight on water. Ag for silver, another ancient name captured in a modern scientific code, a quiet link across millennia. These symbols, these gentle nicknames, H, he, li, o, si, na, ke, fe, au, ag, and all the others for every known element, form a universal language. Scientists in different countries, speaking different tongues, can all understand these simple codes. When they write chemical formulas or discuss atomic structures, these symbols provide clarity and precision. H2O is instantly recognized as water everywhere. NaCl is known as salt, CO2 as carbon dioxide. It's a quiet, shared understanding built on these simple letters. Each symbol is like a tiny key, unlocking the identity of an element. It represents not just a name, but everything we know about that element: its specific number of protons, the way its electrons arrange themselves, its characteristic properties, its place within the grand, ordered pattern of the periodic table. It's a shorthand for a whole miniature universe contained within each type of atom. So, as you rest, imagine this quiet code spreading across the world of elements. See the simple H floating lightly for hydrogen, the gentle he drifting for helium, the round O signifying life-giving oxygen, the strong C for foundational carbon, the surprising Na for sodium, the firm Fe for iron, the glowing Or for gold. Each element, with its unique inner world of protons, neutrons, and electrons, also carries its own simple, quiet label, its scientific nickname. These aren't meant to be confusing or difficult. They are simply tools for clarity, like quiet signposts in the vast landscape of matter. They allow us to talk about the building blocks of the universe with ease and precision. They are part of the order, the quiet elegance we spoke of earlier. Just as the atom itself follows precise rules, the way we name and symbolize these atoms also follows a simple, agreed-upon convention, a gentle system understood across the globe. Think of these symbols now, resting peacefully alongside the elements themselves. They are not the elements, of course, any more than the word water can quench your thirst. But they are pointers, gentle reminders of the underlying reality, the fundamental bricks of everything: H, he, li, b, c, n, o, f, ni, na, mug, al, c, p, s, cl, r, k, ca, phi, cu, zn, ag, or. Each a quiet whisper, a simple name tag for a member of the vast, elemental family that makes up our world, resting now in the stillness, just like you. These quiet symbols, these gentle name tags like H for hydrogen or O for oxygen, they rest beside the idea of the elements themselves, pointing towards something real and fundamental. But beyond the symbol, beyond the name whispered across the world, each element carries something else, something even more specific, something like a secret, internal count. It's a number, a very special number, unique to each and every element in the entire universe. Think of it not just as a name tag, but as a unique address, a specific location in the grand, quiet order of things. Or perhaps, like a tiny, unchanging heartbeat, a rhythm specific to that one kind of atom, a gentle pulse deep within. This number is the element's true identifier, more fundamental even than its name or its symbol. It's a quiet truth held within the very core of the atom. This special number has a name itself, a quiet title given by those who study the atoms closely. It is called the atomic number. It sounds a little formal, perhaps like something from a dusty textbook, but its meaning is wonderfully simple, wonderfully direct, like counting pebbles on a peaceful shore. The atomic number of an element tells us one very important thing. It tells us exactly how many tiny, tiny particles called protons are nestled deep inside the very heart of each atom of that element. Imagine peering, with eyes that could see the infinitesimally small, into the center of an atom. This center is a place called the nucleus. It's the dense, quiet core, the anchor point around which the rest of the atom arranges itself. Inside this core reside the protons. These protons are fundamental pieces of the atom, essential building blocks. They carry a positive electrical charge, a detail we can explore another time, but for now, just think of them as the essential counters, the little beads that we count to know which element we are looking at. The atomic number is simply the count of these protons. 1, 2, 3, 4. Counting them up carefully, precisely, like counting sleeping breaths in a quiet room. Let's think about hydrogen again, the very first element, often shown at the very beginning of those charts called periodic tables. Its symbol is H, a simple letter for a simple beginning. Its special number, its atomic number, is 1. Just 1. That means every single hydrogen atom, anywhere in the universe, whether it's part of the water molecule gently lapping at the edge of a pond, or floating freely in the vast, cold emptiness between stars, or even fueling the fiery heart of our sun, has exactly one proton in its nucleus, just one. That single proton is what makes it hydrogen. It's the defining characteristic, the absolute identifier, its elemental soul, if you will. If an atom has one proton, it is hydrogen. If it has more than one proton, it simply isn't hydrogen anymore. It's something else entirely, a different member of the elemental family. Now, picture helium, the element often found filling party balloons, making them bob and float gently upwards towards the ceiling, light and carefree. Its symbol is He. Helium's special number, its atomic number, is 2, always 2. Deep inside every helium atom, in its quiet, dense core, there are precisely 2 protons. Not 1, not 3, just 2. That count of 2 protons is helium's unique signature, its own special fingerprint. It's what distinguishes it absolutely from hydrogen and from every other element that exists or could possibly exist. 2 protons mean helium. It's that clear, that simple, that fundamental. An atom with 2 protons is helium, and an atom of helium must have 2 protons. And so it goes, element by element, stepping up the number line through the entire family of matter's building blocks. Lithium, a light, silvery metal, carries the symbol Li. It follows helium in this quiet progression. Its atomic number is 3. Every lithium atom, without exception, holds 3 protons tightly within its nucleus. 3 protons define lithium, giving it its unique properties. Then comes beryllium, B, another light metal, with atomic number 4. 4 protons reside in its core, making it distinct from lithium and all others. Boron, B, is next, with atomic number 5. 5 protons nestled together in the nucleus. And carbon, C, the element so wonderfully versatile, so fundamental to life as we know it, the element that forms the soft graphite in your pencil and the incredibly hard sparkle of a diamond, has an atomic number of 6. 6 protons reside in the heart of every carbon atom. Those 6 protons are the essence of carbon, the reason it can form the long chains and complex structures necessary for life. 6 protons make it carbon. This number, this proton count, is not something that changes casually or easily. It's the element's unchanging identity card, stamped onto its very being. An atom might interact with other atoms, sharing or exchanging other, much lighter particles called electrons that swirl like tiny clouds around the outside nucleus. These interactions are what cause chemical reactions, the joining and separating of atoms. An atom might also have slightly different numbers of another kind of particle in the nucleus called neutrons. These neutrons add a little weight but don't change the fundamental identity, creating slightly different versions of the same element called isotopes. But the number of protons in the nucleus, that remains constant for that element. It is the anchor, the bedrock of what the element is. Changing the number of protons would mean changing the element itself into something completely different. Think of it like this. Perhaps, imagine a set of special nested boxes. The smallest box can only ever hold one tiny marble. That box represents hydrogen. The next size box can only ever hold exactly 2 marbles. That's helium. The next, exactly 3 marbles, lithium. The number of marbles each box is designed to hold is fixed, unchangeable. That number defines the box. You know which box you have by counting the marbles it holds. The atomic number, the proton count, is like the fixed number of marbles each element's nucleus holds. 1 marble means hydrogen box, 2 marbles mean helium box, 3 marbles mean lithium box, and so on. The number of protons is the unchangeable capacity, the defining feature for each element. This atomic number, this proton count, is the quiet, unchanging heartbeat of each element, the unique signature that tells us exactly who it is. It dictates its place in the grand order of things, its fundamental identity. But just knowing the name and the core count of each element is only the beginning of the story. Like knowing the names of individual people doesn't tell you about their families, their friendships, or how they behave when they meet others. The true wonder unfolds when we see how these elements are arranged, how they gather together in the remarkable pattern we call the periodic table. Imagine laying out a vast, intricate quilt, stitched together with threads of cosmic dust and starlight. Each patch on this quilt represents an element, placed carefully according to its nature. As our eyes drift across this quilt, we notice not just a long line of patches, but rows stretching across and columns standing tall, running from top to bottom. It's these columns, these vertical arrangements that hold a special kind of magic, a whisper of kinship. Think of them not just as columns on a chart, but as families standing together, generation after generation, sharing a profound resemblance in their ways. These aren't families bound by blood, of course, but by something just as deep in the world of atoms, the way they interact with the world around them, the way they choose to connect or remain aloof. Like siblings who grew up in the same house, played the same games, and learned the same family rules, the elements within a single column often behave in remarkably similar ways. They share a certain character, a predictable pattern of behavior when they encounter other elements. It's as if they inherited a common set of preferences, a shared approach to the dance of chemical reactions. Let's wander gently down the very first column on the left-hand side of our quilt, ignoring for a moment the unique character perched right at the top, hydrogen. We'll come back to that little outlier. Below hydrogen stand lithium, sodium, potassium, and their heavier relatives. This is the alkali metal family. Picture them as perhaps the most outgoing, sociable members of the elemental neighborhood. They are soft, silvery metals, so soft you could cut them with a butter knife, revealing a brief, bright shine before they quickly tarnish, reacting even with the gentle touch of the air. They are eager, almost desperately eager, to connect with others. They possess a certain generosity, always seeming to have something, a tiny particle called an electron, that they are very willing, almost compelled, to share or give away when they meet another element who might accept it. This eagerness makes them incredibly reactive. Drop a tiny piece of sodium or potassium into water, and they don't just sink quietly. They fizz and skitter across the surface, releasing bubbles of gas, sometimes even bursting into a soft lilac or golden flame. It's their way of enthusiastically introducing themselves, of forming a new connection with the water molecules. Lithium, the lightest of this family group, after hydrogen, is a little calmer but shares the same fundamental desire to react and bond. As you move down the column, from lithium to sodium to potassium and further down, this family trait, this reactivity, tends to become even more pronounced. It's like the younger siblings learning from the older ones, their family enthusiasm growing with each generation. They all share this fundamental characteristic, a readiness to give away that one particular electron, allowing them to form strong bonds and become part of something new. They are the builders, the joiners, the elements most likely to reach out first. Now, let's take one step to the right on our quilt, to the second column. Here resides another family, the alkaline earth metals. Think of beryllium, magnesium, calcium, and their kin. They stand right next door to the alkali metals, and they share some family resemblances, but with a slightly different flavor. They are also metals, generally silvery white, and they are also quite reactive, happy to engage with other elements. However, they seem perhaps a little less impulsive than their neighbors in the first column. Imagine them as siblings who are certainly active and enjoy group activities, but maybe they pause for just a moment longer before jumping in. They, too, are generous, but they tend to offer 2 electrons to form connections, not just one. Calcium, for instance, is a vital part of our bones and teeth, forming strong, stable structures. Magnesium burns with a brilliant white light, eager to combine with oxygen. They are reliable participants in the chemical world, forming sturdy compounds. Like the alkali metals, as you travel down this column, the family members generally become more reactive, more willing to engage. Strontium and barium, further down, follow the family tradition with even greater vigor. They are a dependable family, strong and willing to contribute, perhaps just a touch more reserved in their initial approach compared to the effervescent alkali metals next door. They like to play similar joining games, but they bring two players, electrons, to the game instead of one. Let's drift our gaze far across the table now, towards the right-hand side. Skipping over the wide central block for a moment, a fascinating neighborhood in itself, full of versatile characters, we arrive near the edge. Consider the second column from the right, group 17. This is the halogen family: fluorine, chlorine, bromine, iodine, and astatine. If the alkali metals are defined by their eagerness to give an electron away, the halogens are almost their mirror image. They are characterized by a powerful desire to gain just one more electron to feel complete, to achieve a certain kind of atomic stability. Imagine this family as having intense personalities, always searching for that final piece to finish their favorite puzzle. This yearning makes them incredibly reactive, but in a different way than the alkali metals. They aren't looking to give, they are looking to receive, or perhaps more accurately, to share in a way that completes them. Fluorine, at the top, is the most intensely reactive of all elements, a pale yellow gas that combines eagerly, sometimes explosively, with almost anything it touches. Chlorine, a sharp-smelling greenish-yellow gas, is also highly reactive, famous for its use in disinfecting water, where it actively disrupts unwanted microbes. Bromine is a deep reddish-brown liquid, the only non-metal besides mercury to be liquid at room temperature, and it readily evaporates into a similarly colored, pungent gas. Iodine is a purplish-black solid that transforms directly into a beautiful violet vapor when gently warmed, skipping the liquid stage. Despite their different appearances, gas, liquid, solid, they share this core family trait, the drive to acquire one more electron. They often achieve this by pairing up with the generous alkali metals from the far left side of the table. When sodium, from group 1, meets chlorine, from group 17, they react vigorously. Sodium gladly gives away its electron, and chlorine eagerly accepts it. The result is sodium chloride, common table salt. Indeed, the name halogen means salt, former, a name earned by their tendency to react with metals to create salts. They are a family defined by their shared need, their complementary nature to the electron-giving families. Finally, let's look at the very last column on the far right, group 18. This family is known as the noble gases: helium, neon, argon, krypton, xenon, and radon. And they are noble indeed, in the sense of being aloof, serene, and largely uninterested in the reactive mingling that occupies so many other elements. If the alkali metals are eager joiners and the halogens are eager receivers, the noble gases are perfectly content, just as they are. They have achieved a state of quiet stability, a full complement of electrons in their outermost layer, meaning they have no need to give, take, or even share electrons under normal circumstances. Picture them as the quiet, self-sufficient members of the elemental world. They are like siblings who prefer reading quietly in their rooms or pursuing solitary hobbies rather than joining the boisterous games outside. Helium, the lightest after hydrogen, is so light and non-reactive it's used to fill balloons that float effortlessly upwards. Neon, argon, krypton, and xenon are famous for their ability to glow with soft, beautiful colors: red, blue, green, violet, when an electric current passes through them in a sealed tube. They don't burn or react. They simply absorb energy and release it as light, remaining unchanged. They drift through the world, rarely forming bonds with other elements. It takes very special, very forceful conditions to coax them into any kind of chemical reaction. They are the satisfied ones, the complete ones, demonstrating a family trait of profound stability and self-containment. Their presence at the end of each row on the table signifies a kind of completion, a point of rest before a new row, with its new set of electron arrangements, begins. So you see, The columns of the periodic table are far more than just vertical lists. They are lineages, families standing shoulder to shoulder, sharing deep-seated traits in how they approach the world. The alkaline metals, with their eager generosity. The alkaline earth metals, strong and dependable contributors. The halogens, with their intense desire to complete themselves. The noble gases, serene in their self-sufficiency. And many other families reside in the columns between, each with its own characteristic way of behaving, its own set of preferred games to play in the intricate dance of chemistry. This family resemblance arises from something subtle yet profound: the arrangement of the tiny electrons whirling around the nucleus, particularly those in the outermost regions. Elements in the same column tend to have a similar configuration of these outermost electrons, like having the same number of hands available to interact with others, or the same number of empty spaces in their favorite game board. This similarity in their outer structure dictates their chemical personality, leading them to react in similar ways, to form similar kinds of bonds, to exhibit those shared family traits that make the periodic table not just a catalogue, but a rich tapestry of relationships and predictable patterns. It's a quiet story of order and connection, whispered by the elements themselves as they stand together in their family columns, a testament to the underlying harmony of the universe. Now, let us gently shift our gaze. We have walked down the tall avenues of the periodic table, lingered among the family columns where elements stand shoulder to shoulder, sharing their deepest chemical secrets, their inherited ways of interacting, all whispered by the arrangement of their outermost electrons. But the table unfolds in another direction too, doesn't it? Like lines of quiet script written across a page, there are the rows, stretching horizontally from one side to the other. These neat rows invite a different kind of contemplation, revealing another layer of the profound order hidden within the elements. These horizontal rows are known as periods. If the columns spoke of family resemblance, of shared outward behavior, the periods tell a story about inner structure, about the very architecture of the atom itself. Think, if you will, of a sleepy onion, resting peacefully in the cool earth. It grows not just outwards, but in layers, each one carefully wrapped around the one before. First a tender core, then a layer embracing it, then another, and another, each layer adding to its substance, defining its size. The elements in the periodic table are arranged in their periods in a remarkably similar way, based on the layers of electrons they possess. Imagine the tiny nucleus at the heart of an atom, like the very center of that onion. Around this core, the electrons don't just swarm randomly. Instead, they occupy specific regions, almost like designated pathways or orbits, often called shells or energy levels. These shells are layered, one outside the other, much like the layers of our sleepy onion. Each shell can only hold a certain number of electrons before it is considered full, comfortably occupied. The first period, the very top row of the table, is the simplest of all. It contains just two elements, hydrogen and helium. These elements are like the innermost core of the onion, possessing electrons only in the very first, the closest energy shell to the nucleus. Hydrogen, with its single electron, is like the beginning of that first layer. Helium, with two electrons, completes this first shell, making it feel stable and content, much like the first complete layer around the onion's heart. This first shell is small, intimate, holding only these two occupants. Then, as we move down to the second row, the second period, we begin a new layer. It's as if our onion is adding its next layer of growth. Elements in this second period, starting with lithium on the far left and journeying across to neon on the far right, all have electrons occupying two main energy shells. They have the completed inner shell, like helium's, and now they are beginning to fill the second shell, the next layer outwards. Lithium starts this process gently, placing just one electron in this new outer second shell. As we drift across the row, through beryllium, boron, carbon, nitrogen, oxygen, fluorine, each element adds one more electron to this second shell. It's like carefully placing treasures into designated spots within this expanding layer. Carbon, midway, has partially filled this shell, giving it a unique versatility. Fluorine, near the end, has almost filled it, leaving it just one electron short, making it intensely eager to find that final piece. Finally, we reach neon, the noble gas, at the end of this row. Neon has successfully filled this second shell completely. With both its inner shell and its second shell full, neon achieves a state of serene completeness, much like our onion having finished a perfect, smooth layer. Every element in this second row, from lithium with its single outer electron to neon with its full outer shell, shares the fundamental characteristic of having its outermost electrons residing in that second energy level. They all possess two layers in their electron structure. Dropping down again, we arrive at the third period, the third row across the table. Can you guess the pattern? Yes, just as our onion adds another layer, so do these elements. Starting with sodium, Na, and ending with argon, R, every element in this third period has electrons distributed across three main energy shells. They have the full first shell, the full second shell, and now they are populating the third shell, the next layer out from the center. Sodium begins this row by placing its single, outermost electron into this third shell. Magnesium follows with 2. Then, as we move across through aluminum, silicon, phosphorus, sulfur, and chlorine, this third shell gradually fills, electron by electron. Chlorine, like fluorine above it, is just 1 electron shy of filling this third outer shell. And argon, the noble gas concluding this period, achieves that satisfying fullness in its outermost shell. Despite their different chemical personalities, sodium being an eager alkali metal, chlorine a reactive halogen, argon a self-sufficient noble gas, they all share the common structural trait of having 3 electron shells. Their outermost electrons, the ones involved in most chemical interactions, are all playing their roles within that third layer. This pattern continues as we descend further down the table, row by row, period by period. The fourth period introduces the fourth electron shell. Elements like potassium, K, and calcium, K, start filling this fourth layer. This row is longer, as more complex electron arrangements become possible, including the filling of inner sublevels, which gives rise to the transition metals nestled in the center of the table. But the fundamental principle holds. The period number tells us the highest main energy level, the outermost primary layer, that contains electrons for an element in that row. Elements in the fifth period are building upon 5 shells, those in the sixth period utilize 6 shells, and so on. Each new row downwards signifies the beginning of a new principal electron shell, like adding another encompassing layer to our ever-growing onion. So, while the columns tell us about the number of electrons in the outermost shell, the key to chemical family behavior, the rows tell us which shell is the outermost one. They speak of the overall size and energy structure of the atom. An atom of sodium, period 3, and an atom of potassium, period 4, are in the same column, the alkali metals, because they both have 1 electron in their outermost shell, making them similarly reactive. But potassium is in the row below sodium because its single outer electron is in the 4th shell, 1 layer further out than sodium's, which is in the 3rd shell. This makes the potassium atom larger, its outermost electron held a bit less tightly, residing in a higher energy level, further from the nucleus's pull, like being on a more distant layer of the onion. Think about drifting across a single row, say the 3rd period from sodium to argon. We start on the left with sodium, a metal eager to give away its lone electron in that 3rd shell. As we move right, adding protons to the nucleus and electrons to that same 3rd shell, the character of the elements gradually shifts. We move through metals like magnesium and aluminum, then encounter silicon, a metalloid sitting on the fence between metallic and non-metallic behavior. Then come the nonmetals, phosphorus, sulfur, chlorine, elements that are increasingly interested in gaining electrons to complete their 3rd shell rather than losing them. Finally, we reach argon, the noble gas, with its 3rd shell perfectly filled, aloof and chemically inactive. All along this journey across the row, the electrons were being added to the same outermost shell, the 3rd layer. The increasing positive charge of the nucleus pulls more strongly on these electrons within that same shell, which often causes the atoms to actually become slightly smaller as we move from left to right across a period, pulling that outer layer in a little tighter. It's a subtle tightening within the same layer of the onion. The rows, therefore, map out the gradual filling of these energy shells. They represent stages of atomic construction, layer by layer. Each period begins with an element placing its first electron mass into a new outermost shell, often resulting in a reactive metal. Each period typically ends with a noble gas, an element that has achieved a stable configuration by completely filling its outermost shell, or relevant subshells. The journey across a period is a story of transition, of moving from an electron configuration that is far from stable to one that is serenely complete, all within the confines of the same principal energy level, the same onion layer. These shells aren't rigid physical barriers, of course, but rather regions of probability, spaces where the electrons are most likely to be found, humming with energy. The layered shell model, like our onion, is a way to visualize this underlying quantum structure. It helps us understand why the table has the shape it does, why certain elements appear where they do, and why properties change in predictable ways not just down the columns, but also across the rows. So, the periodic table reveals its elegance in both directions. The columns are the families, defined by their shared outer electron configurations, leading to similar chemical behaviors. The rows, the periods, represent the building up of electron shells, layer upon layer, defining the energy level of those outermost electrons and influencing properties like size and the gradual shift from metallic to non-metallic character. It's like reading a beautifully organized book, where the chapters, periods, introduce new levels of complexity, and within each chapter, the paragraphs, elements across a row, develop a theme, while recurring characters, families in columns, appear throughout the narrative, exhibiting their consistent personalities. It's a quiet, layered story, told in the language of electrons and energy shells, unfolding row by neat row across the table, another testament to the calm, underlying order of the universe. As we trace these patterns, letting our gaze drift across the elegant structure of the table, following the neat rows like pathways and the columns like quiet avenues, our attention settles upon the largest realm within this elemental kingdom. It stretches far and wide, occupying the vast majority of the landscape, a broad territory filled with members of a particular character. These are the metals, the most numerous inhabitants of the periodic table. They fill the center, lean heavily towards the left-hand side, and even reach down into those separate rows floating peacefully below the main continent. If the table is a grand castle, meticulously organized, then the metals are its most prominent residents, its steadfast guardians. Imagine them, if you will, as an order of knights, not the clamoring, jousting kind, full of restless energy, but rather sturdy, sleepy knights, standing watch with a quiet strength. They are known, first and foremost, for their gentle gleam, a characteristic luster that catches the light. Think of moonlight spilling across a calm lake, or the soft reflection in a polished shield left leaning against a castle wall in the quiet hours. This shininess isn't a boastful glare, but a calm announcement of their presence. It speaks of surfaces that are smooth and ordered at a tiny, invisible level, surfaces that like to gather the light and turn it back towards our eyes in a soft, silvery shimmer, or sometimes a warm, golden glow, or the blush of copper. It's as if they hold a little bit of captured daylight within them, releasing it gently when light touches them. This ability to reflect light, to shine, is one of the first things we notice, a shared trait among this vast family, like a common uniform worn with quiet dignity. And they are strong, these metallic knights. They possess an inherent solidity, a resilience that makes them reliable. They form the foundations, the structures, the very bones of many things we know. Think of the strong, silent arches of a bridge holding steady over flowing water, or the frame of a tall building reaching patiently towards the sky. This strength isn't aggressive, it's the strength of endurance, of holding firm. Our sleepy knights stand shoulder to shoulder in orderly ranks, forming crystalline structures, neat repeating patterns invisible to our eyes but conferring upon them their dependable nature. They link arms, metaphorically speaking, sharing their outermost electrons in a way that creates a powerful, collective bond, a sea of shared energy that flows between them like a quiet understanding. This sharing holds them together firmly, allowing them to resist being easily pulled apart or broken. They are the castle walls themselves, the sturdy gates, the reliable framework upon which other things can rest or depend. They don't easily crumble, they endure. Their sleepiness isn't laziness, but a kind of calm readiness. They stand their posts, largely unreactive in their pure forms compared to some of the more excitable elements found elsewhere on the table. Many of them are content to simply be, solid and present. Think of a great iron gate, standing for centuries, weathered but fundamentally unchanged, its strength a quiet testament to its nature. Or consider a piece of gold, soft for a metal yet incredibly resistant to tarnish, remaining bright and lustrous through the ages, a sleepy knight in gleaming ceremonial armor, untouched by the passage of time or the bustle of the world around it. Of course, within this vast order of knights, there is diversity. Not all metals are exactly alike, just as knights might wear different armor or carry different standards. Some, like the alkali metals found on the far left edge of the table, are surprisingly soft, almost like hardened butter, and much more eager to react, like knights newly woken and quick to engage. They are still metals, shiny when freshly cut, but their strength is of a different kind, more chemically energetic. Then there are the familiar, sturdy ones, like iron, the backbone of industry, strong and reliable, though perhaps prone to rusting if left unprotected, like a knight whose armor needs tending. There is copper, with its warm reddish glow, a friendly metal often used for wiring because it allows energy to flow through it so easily. Like a trusted messenger carrying signals swiftly and silently through the castle corridors. And silver, brighter and even better at carrying those signals, though perhaps a little more precious. Gold, again, soft and heavy, valued for its enduring beauty and resistance to corrosion. The noble knight, whose value lies in its steadfastness and incorruptibility. Aluminium, surprisingly light for its strength, like a knight in cleverly crafted, lightweight armor, useful for building things that need to be both strong and mobile. These metallic knights occupy the broad plains and rolling hills of the periodic table's central and leftward regions. Look at the table, and you see their domains stretching out, columns upon columns, rows upon rows, a vast fellowship. This sheer expanse tells you how fundamental they are to the very fabric of matter as we know it. They are not rare exceptions, they are the common citizens, the foundational population of the elemental world. Their shared electron C, the source of their strong bonds, also grants them other remarkable abilities, performed with the same quiet efficiency. They are excellent conductors of heat and electricity. Imagine warmth spreading through a metal spoon left in a cup of hot tea, or the silent, invisible flow of electricity through a copper wire bringing light to a lamp. This isn't a chaotic rush, but an orderly transfer. The freely moving electrons, that shared C surrounding our nightly atoms, can easily carry thermal energy from one place to another, passing it along like a whispered message down a line of guards. Similarly, they allow electrical current, a flow of electrons, to move through them with very little resistance. It's like having perfectly smooth, wide corridors throughout the castle, allowing energy and messages to travel effortlessly from one end to the other. This quiet conductivity is a hallmark of the metallic nature, a consequence of their communal electron sharing. Furthermore, these sturdy knights possess a surprising flexibility. While strong, they are often not brittle. Many metals exhibit malleability, meaning they can be hammered or pressed into thin sheets without shattering. Think of gold leaf, beaten incredibly thin, yet still retaining its golden character. Or aluminium foil, pressed into sheets we use every day. They also show ductility, the ability to be drawn out into thin wires. Copper wire is a perfect example. Imagine gently stretching a piece of warm toffee. The metal atoms can slide past one another, rearranging their positions without breaking the overall metallic bond, thanks again to that fluid sea of electrons holding everything together. Our sleepy knights can shift formation, rearrange their ranks under pressure, adapting their shape without losing their cohesion or their fundamental strength. They can be shaped for specific purposes, bent into useful forms, drawn into fine threads, all while maintaining their integrity. It's a yielding strength, an adaptability that makes them incredibly versatile. So, these are the metals, the shiny members, the sturdy, sleepy knights of the periodic table. They stand in vast numbers, defined by their gentle luster, their quiet strength, their ability to share warmth and energy, and their capacity to be shaped without breaking. From the mighty iron beams holding up structures to the delicate gold leaf adorning a treasured object, from the copper wires carrying silent messages of electricity to the silvery sheen of a simple spoon, they are all around us, fundamental components of our world. They are the dependable majority, the quiet protectors in the elemental castle, their presence a constant, reassuring reminder of the underlying order and resilience woven into the fabric of the universe. They stand their watch, gleaming softly, holding firm, a vast, calm collective at the heart of the periodic table story. But not all the residents of this elemental kingdom share that metallic gleam, that yielding strength. If the metals are the vast, shining majority, the sturdy knights holding the center ground, then scattered in quieter corners, mostly residing off to one side of the great table, live another group. They are fewer in number, yet wonderfully diverse in their nature, a collection of quiet contrasts to their gleaming neighbors. These are the non-metals, and they possess a different kind of character altogether. They don't stand in neat, reflective ranks. They don't readily share the flow of warmth or the river of electrons in the same easy way. They are the individuals, the exceptions, the elements that define themselves often by what they are not. Imagine turning your gaze from the ranks of silvery, golden, or coppery knights, and finding instead perhaps nothing visible at all. For many of these non-metals exist not as solid forms under everyday conditions, but as gentle, invisible gases. Think of the air that fills this very room, the soft breath you are taking right now. It's composed mainly of non-metals, nitrogen and oxygen, drifting unseen all around us. They have no inherent shine, no solid form we can easily grasp. They are like quiet whispers, filling the space without announcing their presence in a visible way. Hydrogen, the lightest element of all, is another such ethereal being, content to float, unseen, unbound. These gaseous non-metals are free spirits. They don't cling together in rigid, ordered structures like the metals. They drift apart, expanding to fill whatever space contains them, like unseen currents flowing through the world. Helium, another non-metal gas, is so light it lifts balloons towards the sky, yearning for the upper reaches, a testament to its barely there presence. Neon glows with a fiery color when electricity passes through it, but otherwise, it too is just an invisible component of the air, alongside its other noble gas relatives like argon and krypton. They possess no luster, cannot be hammered or drawn into wires. You cannot shape a breath of air or polish a whisper. They simply are, present and essential, but in a form that is diffuse, transparent, almost ghostly compared to the solid certainty of metals. They are the quiet atmosphere, the background presence, essential for life itself, yet lacking the tangible, reflective qualities we associate with the metallic realm. They float, they mingle, they remain unseen, their existence a gentle contrast to the solid world. But not all non-metals are invisible gases. Some do take solid forms, yet even here, they stand apart from the metals. Wander further into their domain, and you might encounter substances that are far from shiny. Think of carbon, not in its rare, exceptionally hard form as diamond, but in its more common guises, like charcoal, dark and dusty, or graphite, the soft grey material in a pencil lead. While graphite might have a slight sheen, it's a dull luster compared to silver or gold, and it's remarkably soft and slippery. If you were to strike a piece of charcoal with a hammer, it wouldn't flatten or bend like a metal. It would simply shatter into smaller pieces, crumbling into dust. This brittleness is a hallmark of many solid non-metals. Consider sulfur, another solid non-metal. It often appears as pale yellow crystals or powder. It has no metallic shine, just a soft, chalky or perhaps slightly resinous appearance. Like charcoal, it is brittle. Tap it, and it breaks. There is no yielding, no reshaping, only fracturing. It cannot be drawn into wires or hammered into sheets. Its strength, such as it is rigid and fragile. It holds its form until it breaks completely. Phosphorus is another character in this group, sometimes appearing as a waxy white solid that glows faintly in the dark, a property unique and quite unlike metals, or as a more stable red powder. Again, it is brittle, lacking the internal give that allows metals to deform. These solid non-metals are more like hardened earth, or dry clay, or perhaps pieces of colored rock, opaque or translucent, sometimes crystalline, but rarely reflective, and always ready to crumble rather than yield. Their surfaces don't gleam back at you with reflected light in the way a polished metal surface does. They tend to absorb light, or scatter it softly, giving them dull, earthy, or sometimes brightly colored but non-reflective appearances. They feel different to the touch too. Metals often feel cool because they quickly draw heat away from your fingers. Solid non-metals, however, tend to feel less cool, less eager to share warmth. They are often poor conductors of heat. Think of the handle on a metal cooking pot. It's often made of wood or plastic, materials rich in non-metals like carbon and hydrogen. Precisely because these materials don't readily transfer the heat from the pot, your hand. They act as insulators, barriers to the flow of heat. This reluctance to conduct extends to electricity too. While metals welcome the flow of electrons through their structure, allowing electricity to pass easily, non-metals generally resist this flow. The electrons in non-metals are typically held more tightly by individual atoms or shared in strong, localized bonds between atoms. There isn't that fluid sea of electrons found in metals, ready to move and carry a current. So, non-metals act as electrical insulators. They are the materials used to coat electrical wires, like the plastic or rubber sheath around a copper wire, preventing the electricity from escaping and keeping it directed along the metallic pathway. They wrap the energetic flow, contain it, rather than participating in it. They provide the quiet boundaries, the necessary containment for the energetic pathways carved through metals. There is even one non-metal that exists as a liquid at room temperature, much like the metal mercury. But where mercury is a bright, silvery, heavy liquid, the non-metal bromine is a deep, reddish-brown liquid, volatile and quite distinct. It stands alone, a liquid in a family dominated by gases and brittle solids, further emphasizing the sheer variety within the non-metal group compared to the more uniform metals. So, these non-metals form a fascinating counterpoint to the metals. They are defined not by a shared set of positive characteristics like luster or conductivity, but often by the absence of these metallic traits. They are the other, the diverse collection that doesn't fit the metallic mold. Some float unseen as gases, essential components of the air we breathe, light and formless. Others exist as solids, but solids that are typically dull, brittle, and poor conductors of heat and electricity, crumbling rather than yielding, insulating rather than conducting. They are yellow powders, dark dust, invisible breaths, colorful crystals that shatter. They are found in the air, in rocks and minerals, and they are fundamental building blocks of life itself. Carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur are central to all living organisms. They don't possess the sleepy, sturdy uniformity of the metallic knights. They are more like a scattered collection of hermits, scholars, artists, and airy spirits dwelling apart. Each has its own distinct personality, its own unique properties. They are the quiet contrasts, highlighting the very nature of metals by being so different. Their story is one of variety, of insulation rather than conduction, of brittleness rather than malleability, of dullness or transparency rather than luster. They bring balance to the periodic table, a necessary counterweight to the vast metallic collective, reminding us that the elemental world is rich with diversity, encompassing not just the strong and shining, but also the subtle, the brittle, and the unseen. They may be fewer, but their roles are just as crucial, their quiet presence shaping our world in ways just as profound as their metallic brethren. They are the other side of the elemental coin, essential parts of the whole, completing the picture of the kingdom of elements with their unique and varied characters. And then, if you let your gaze drift all the way across the table, past all the varied non-metal characters, the solids, the liquids, the reactive gases, you arrive at the very edge, the far right-hand column. It feels like reaching a quiet shoreline after a long journey through bustling lands. Here dwell a very special group of elements, the picture of contentment and peace. These are the noble gases, residing together in Group 18, a family quite unlike any other. They live in a serene state, like gentle hermits meditating on a calm mountaintop, perfectly happy in their own company. They are the calm and happy gases, the embodiment of elemental tranquility. Imagine them lined up in their column, one below the other, like a row of perfectly smooth, luminous pearls, each complete and self-contained. They have no need to reach out and grasp at their neighbors, no desire to share or borrow or fight for attention. Why? Because their innermost secret, the source of their profound peace, lies in their structure. Think of the electrons orbiting the nucleus like tiny planets around a sun. For most elements, the outermost path, the valence shell, feels incomplete. It might have too few electrons, leaving it feeling empty and wanting more, or perhaps almost full, making it desperately seek just one or two more to feel whole. This incompleteness drives them to interact, to bond, to react, always searching for stability. But the noble gases are different. Each one of them, from the lightest to the heaviest, has achieved a state of perfect balance in its outer shell. It's completely full, perfectly satisfied. Imagine a perfectly drawn circle, with no beginning and no end, utterly complete. Or perhaps think of a cup filled precisely to the brim with clear, still water, not a drop more needed, not a drop less desired. This fullness brings a deep sense of calm. They have everything they need within themselves. There are no empty spaces yearning to be filled, no extra electrons feeling restless and eager to leave. They are whole. And because they are whole, they feel no compulsion to join the busy dance of chemical reactions that occupies so much of the rest of the periodic table. They can simply be. They float through the universe, serene and detached, rarely forming compounds with other elements. It's not out of arrogance, this nobility, but out of simple, quiet self-sufficiency. They are the silent observers, the peaceful inhabitants of the elemental kingdom's most tranquil neighborhood. Let's meet them, gently, one by one, as they reside in their peaceful column. At the very top, the lightest of them all, is helium. Its symbol is He. Helium is so light, so ethereal, it seems barely tethered to the earth. Think of a child's balloon, tugging gently upwards, wanting to float away into the vast blue sky, silent and free. Helium is the second most abundant element in the entire universe. After hydrogen, it's born in the heart of stars, in the fiery fusion that lights the cosmos, yet its nature is one of utter calm. It fills giant stars, yet here on Earth, it lifts airships and weather balloons with a quiet, invisible strength. It doesn't burn, it doesn't react, it simply lifts, floats, and exists. A whisper of the sun's serene power trapped in a bubble, or dispersed invisibly in the air around us. Though our atmosphere holds only tiny traces of it, it's the quiet breath of the cosmos. Just below helium sits neon. Nay, neon is perhaps the most famous for its gentle, captivating glow. When electricity passes through neon gas sealed in a tube, it doesn't flash or spark aggressively. It emits a soft, warm, reddish-orange light. Think of the gentle hum and welcoming glow of a sign on a quiet street corner as dusk settles, a warm beacon in the cool air. It's a color that feels friendly and inviting, yet the element itself remains aloof, content in its glass enclosure, sharing only its light, not its substance. It doesn't need to shout. Its quiet glow is enough. It exists, like its lighter sibling helium, in the air around us, a tiny fraction of every breath we take, unnoticed until coaxed into revealing its beautiful, peaceful light. Next in the column comes argon, R. Its name comes from the Greek word argos, meaning inactive or lazy, a name given due to its profound reluctance to react with anything. Argon is much more abundant in our atmosphere than helium or neon. In fact, it's the third most common gas in the air we breathe, making up almost 1%. Yet, despite its prevalence, it goes utterly unnoticed. It is colorless, odorless, tasteless, the epitome of unobtrusive existence. It's like the quiet air filling a room, present everywhere but drawing no attention to itself. Its stillness, its inertness, is its gift. We use argon precisely because it doesn't interfere. It fills the space between the panes of double-glazed windows, acting as an invisible, insulating blanket, quietly keeping the warmth in and the cold out. It's used to protect precious old documents, surrounding them with an atmosphere that won't tarnish or degrade them. It fills light bulbs, protecting the delicate filament from burning out too quickly. Argon is the silent guardian, the invisible protector, happy to simply fill the space and keep the peace. Beneath argon, we find krypton Kurnia. Its name, fittingly, means the hidden one. Krypton is rarer still than argon, hiding even more effectively in the vastness of the atmosphere. Like its siblings, it is colorless and odorless, a quiet ghost in the air. But krypton, too, can be coaxed into producing light, often a whitish or sometimes greenish glow, different from neon's warm red. Its light is often used in high-powered lamps, like those found in lighthouses, cutting through fog with a steady, reliable beam, or in certain types of lasers. It's a hidden light, revealed only under special circumstances, a quiet mystery dwelling deep within the air, another testament to the peaceful but present nature of these noble elements. It waits patiently, hidden, until called upon to shine its specific, quiet light. Deeper still in the column rests xenon, Ze. Xenon means the stranger, named because it was unexpected, another hidden gas found lurking in the residue after liquefying air. It is even rarer than krypton, a true stranger in our atmosphere. Xenon is heavier, denser, and though still remarkably inert, it was the first noble gas persuaded, under very special and demanding conditions, to form chemical compounds, showing that even the most contented hermits might, very occasionally, interact if the circumstances are extraordinary. But mostly, xenon maintains its noble calm. When excited, it produces a beautiful, bright, bluish light, used in specialized lamps like high-intensity headlights that pierce the darkness, strobe lights that flash with brilliant intensity, and lamps that simulate natural sunlight. It also has a surprising use in medicine as an anesthetic, capable of inducing a state of calm unconsciousness, a testament perhaps to its inherently peaceful nature, lending its stillness to others. Xenon is the quiet stranger with a hidden, powerful light and a calming touch. Below xenon comes radon, Rn. Radon is different from its lighter siblings in a significant way. While it shares the same peaceful electron configuration, the complete outer shell that defines the noble gases, its nucleus, the very heart of the atom, is unstable. Radon is radioactive. It is born from the slow decay of heavier elements, like uranium and thorium, deep within the Earth. Being a gas, it can seep gently out of the ground and into the air, particularly in basements or enclosed spaces. It is heavy, the densest of the naturally occurring gases. Its presence reminds us that even in this column of serene stability, the universe holds processes of change and decay. Radon is like a very old, very wise being, complete and calm in its outer form, but carrying within its core the knowledge of transformation, slowly releasing energy as it changes into other elements. It doesn't interact chemically, maintaining its noble aloofness, but its very substance is in quiet flux. It's a gentle, radioactive whisper from the Earth's depths, part of the family, yet unique in its transient nature. Finally, at the very bottom of this tranquil column lies oganesson, Oganesson is not found in nature. It is a synthetic element, created by humans in powerful particle accelerators, existing for only the tiniest fraction of a second before decaying. It is the heaviest element known. Its existence, however fleeting, confirms the beautiful pattern of the periodic table, showing that even here, at the extreme edge of known elements, the column of noble gases finds its completion. It's like a final, faint echo of the peace and stability that characterizes this group, a momentary testament to the enduring pattern of completeness, even when stretched to the limits of possibility. So, this is the family of noble gases, residing peacefully on the far right edge of the periodic table: helium, neon, argon, krypton, xenon, radon, and the fleeting oganesson. They are the calm ones, the happy ones, content in their own completeness. They are mostly invisible, often hidden, yet they fill our universe, our air, our lights, with their quiet presence. They don't seek connections because they are already whole. They are the gentle counterpoint to the reactive elements nearby, the halogens just next door, so desperate for one more electron. or the alkali metals on the far left, so eager to give one away. The noble gases watch this elemental drama unfold from their serene vantage point, uninvolved, undisturbed. They are like still pools reflecting the sky, while nearby streams rush and tumble. They bring a sense of calm completion to the entire periodic table, a reminder that peace and self-sufficiency are also fundamental states of being in the rich tapestry of the elements. They drift, they glow softly, they fill the quiet spaces, perfectly content just to be themselves, the calm and happy gases. While these noble gases drift in their quiet contentment, holding on to their completeness like a cherished secret, the rest of the universe tells a different story. It's a story not of stillness, but of becoming. A story of creation, unfolding over unimaginable stretches of time, in places of incredible heat and light. The elements that make up our world, the air we breathe, the ground beneath our feet, the very substance of our bodies, they weren't always here, they had to be made. And their birthplace, the grand cosmic kitchen where the ingredients of reality were cooked, was inside the stars. Imagine looking up into the vast, dark stillness of the night sky. Those tiny points of light, seemingly so calm and distant, are immense furnaces. They are where the universe performs its slow, patient alchemy. It all began simply, long, long ago, with the lightest and most basic elements, born from the very first moments after the universe itself began. Hydrogen, element number 1, the simplest atom of all, just a single proton and a single electron, filled the early cosmos like a thin, invisible mist. Alongside it was helium, element number 2, already possessing that noble gas stability, a quiet hint of the peace to come. These were the primordial ingredients, the starting point for everything else. Deep within the hearts of the first stars, gravity began its gentle but relentless work. It pulled the abundant hydrogen atoms closer and closer together. As the pressure and temperature climbed impossibly high, reaching millions of degrees, something truly magical began to happen. Hydrogen atoms, under this immense insistence, started to fuse together. It wasn't a violent clash, but a transformation, a merging of identities. 4 hydrogen atoms would eventually combine, through a series of steps, releasing a tremendous amount of energy, the very light and heat that makes stars shine, and forming a single atom of helium. This is the first step in stellar cooking, the fundamental process that powers stars like our own sun for billions of years. It's a slow, steady burn, converting the simplest element into the next, bathing nascent solar systems in gentle warmth. But the universe, in its quiet ambition, didn't stop there. As stars age, particularly those much larger and more massive than our sun, they begin to run low on hydrogen fuel in their cores. Gravity continues its inward pull, causing the core to contract further and heat up even more. Now, helium atoms, the product of the first fusion stage, find themselves under immense pressure. When the temperature reaches hundreds of millions of degrees, helium atoms begin to fuse. 3 helium atoms can combine to form an atom of carbon, element number 6. Think of carbon. It's the element of life as we know it. It's in the soft graphite of your pencil, leaving quiet grey marks on paper. It's in the incredibly hard, sparkling diamond, formed under immense pressure deep within the Earth, but originating from stellar cores nonetheless. Most importantly, carbon atoms have a remarkable ability to link together, forming long chains and complex rings, creating the intricate molecular structures that form the basis of trees, flowers, animals, and us. This versatile element, the backbone of life, was forged in the heart of aging stars, a testament to the creative power brewing in those distant celestial bodies. As the stellar furnace grows hotter still, more fusion processes become possible. If a carbon atom captures another helium atom, it transforms into oxygen, element number 8. Take a slow, deep breath. Feel the air fill your lungs, the gentle expansion in your chest. That invisible substance giving you life, the oxygen you breathe, makes up about 1/5 of the air around us. It combines with hydrogen to form water, the clear, cool liquid that covers so much of our planet and fills our bodies. Oxygen is fundamental, essential, quietly sustaining. And this gentle, life-giving element was created deep inside massive stars billions of years ago. It's a quiet miracle, this process. Helium and carbon fusing together in the stellar crucible to create the very gas that allows us to draw breath, moment by moment. The star burns steadily, patiently, layer by layer, cooking up heavier elements in its core. Oxygen, neon, magnesium, silicon, elements that form the rocks and minerals of planets like ours, are built up in successive stages as the star's core gets hotter and denser. Imagine the star now like a cosmic onion, with different layers where different elements are fusing. Hydrogen still burns in the outer shells, helium fuses in a layer beneath that, carbon in the next, then oxygen, and so on. Each stage requires higher temperatures and pressures, driven by the relentless pull of gravity. This process continues, building heavier and heavier elements, until it reaches iron, element number 26. Iron is a special element in this stellar story. It's incredibly stable. Fusing iron atoms together doesn't release energy like the fusion of lighter elements. Instead, it requires energy. So, when the core of a massive star becomes filled with iron, the fusion process that has supported the star against gravity for millions or billions of years suddenly stops. The furnace goes out. Iron is like the final ash of this normal stellar burning process. Think of iron, its strength, its solidity. It forms the core of our own planet, generating the magnetic field that shields us from harmful solar radiation, a quiet guardian born from the end of a star's long life. It gives the rich red color to some soils and rocks, a constant, subtle reminder of its stellar origins. It's the anchor point in the sequence of stellar fusion. But the story doesn't end with iron's quiet stability. When fusion ceases in the core of a very massive star, gravity wins decisively. The star's core collapses catastrophically in a fraction of a second, and then rebounds in an unimaginable explosion, a supernova. For a brief period, a single exploding star can outshine an entire galaxy. It's not just a destructive event, it's a moment of intense, rapid creation. The incredible energies released during a supernova forge elements heavier than iron. The controlled cooking of the star's life gives way to a final, fleeting, furious burst of creation. And it's in these moments, or perhaps in the even more energetic collisions of incredibly dense stellar remnants, called neutron stars, that some of the most precious and rare elements are born. Think of gold, element 79. Feel its comforting weight in your hand if you have a piece of gold jewelry, perhaps a smooth, cool ring, or a delicate chain. See its soft, gentle gleam, a color unlike any other, like captured sunlight. Gold is rare, treasured through history for its beauty and incorruptibility. It doesn't rust or tarnish easily, it endures. This beautiful, heavy, precious metal was created in the heart of these cataclysmic cosmic events, a supernova's final brilliant flash, or the spiraling dance and merger of neutron stars. The conditions needed are so extreme, the events so rare, that gold remains scarce throughout the universe. Every atom of gold on Earth, whether nestled deep underground waiting to be discovered or fashioned into a sleepy treasure, is a tiny, glittering echo of one of the most powerful events the cosmos can produce. It's a whisper of starlight made solid, a tangible piece of cosmic history resting quietly in our world. Silver, too, with its cool, bright shine, and platinum, dense and enduring. These precious metals are also forged in these spectacular stellar finales. The supernova doesn't just create these heavy elements, it also scatters them, along with all the lighter elements cooked during the star's lifetime, the carbon, the oxygen, the iron, far out into space. This enriched material mixes with interstellar gas and dust clouds, the very clouds from which new stars and planetary systems will eventually form. Think of the calcium in your bones, giving them quiet strength, or the silicon that makes up the sand on a peaceful beach and the rocks beneath your feet. These too were forged in stars. The potassium that helps your nerves carry gentle signals, the sodium that balances the water in your body, stardust. The nitrogen in the air and in your DNA, stardust. Element by element, the periodic table comes alive with stories of cosmic origin. From the simplest hydrogen atom to the fleeting glimpse of oganesson, each has its place, its history. So, as you rest, breathing in the oxygen born in a long-dead star, perhaps wearing a tiny piece of gold forged in a cosmic explosion. Remember that you are connected to the universe in the most intimate way possible. The elements that make up your body, the world around you, the ground, the air, the water, were all meticulously crafted in the hearts of stars and scattered across the cosmos. We are, quite literally, made of stardust. The universe is not just out there, distant and remote. It is within us. The calm contentment of the noble gases is one part of the story, the quiet completion. But the journey of the other elements, their creation in fiery stellar cores and their dispersal through space to eventually form planets and people, is another part, a story of transformation, connection, and the slow, gentle unfolding of cosmic potential. It's a quiet reminder, as you drift towards sleep, that even in stillness, you are part of a grand, ongoing cosmic narrative, woven from the very fabric of the stars. And so, holding this quiet truth close, that we are woven from the threads of stars, that the universe resides not just above but within us, we turn our gaze towards the map that helps us navigate this profound connection. We look towards the periodic table of elements, that familiar grid hanging in classrooms and laboratories, often glanced at, sometimes memorized, but perhaps not always truly seen for the wonder it holds. Why do we love this chart? Why does this seemingly simple arrangement of letters and numbers evoke such a deep sense of admiration, even affection, among those who spend time contemplating it? It isn't just a list, you see. It's far more than that. It's a story, a prophecy, a family tree, and a landscape, all captured in one elegant design. Imagine, if you will, stepping into a vast, quiet library. Not one filled with books written by human hands, but a library of existence itself. Each element is a fundamental character, a unique voice in the story of the cosmos. Before the periodic table, it was as if these characters were wandering aimlessly, their connections unclear, their relationships hidden. We knew of gold's quiet gleam, iron's steady strength, oxygen's vital breath, but how they related, why they behaved as they did, remained largely mysterious. The genius of the table, particularly as Dmitry Mendeleev and others began to piece it together, was like discovering the library's intricate cataloging system. Suddenly, there was order. There were shelves, sections, logical groupings. Elements weren't just scattered, they belonged somewhere, nestled among neighbors with similar traits, part of larger families sharing deep-seated characteristics. This inherent order is, perhaps, the first reason for our quiet affection. The table is visually calming in its regularity. The neat rows, called periods, stretch across like peaceful horizons. The columns, called groups, stand tall and orderly like ancient pillars holding up a silent temple of knowledge. There's a rhythm to it, a predictability that soothes the mind. It suggests that the universe, at its most fundamental level, is not chaotic but harmonious, governed by underlying principles that we can actually discern. It whispers of a deep logic woven into the fabric of reality. Like looking at a perfectly tiled mosaic or the intricate repeating patterns on a seashell, the structure itself is a source of quiet beauty. But the table is more than just a pretty arrangement. It holds a gentle kind of magic, the magic of foresight. Because the pattern was so strong, so consistent, Mendeleev could see gaps in his arrangement. He could see places where an element should be, based on the properties of its neighbors above, below, and to the sides. It was like looking at a beautifully woven tapestry with a few threads missing, and knowing, just by the surrounding colors and textures, what the missing threads must look like. He didn't just predict that elements existed to fill these gaps, he described them. He spoke of their weight, their color, how they might feel to the touch, how readily they would join with other elements, all before they had ever been seen or isolated. Imagine the quiet confidence, the deep trust in the underlying order required to make such claims. And then, imagine the gentle satisfaction, years later, when elements like gallium, germanium, and scandium were discovered, fitting into their designated spaces almost perfectly, behaving just as the pattern foretold. It was like finding lost keys exactly where you knew they ought to be, a quiet affirmation that the map was true. This predictive power isn't loud or boastful. It's a quiet testament to the profound coherence of the natural world, a coherence the table allows us to glimpse. Then there is the way the table reveals relationships, like uncovering the subtle family resemblances in a large, extended family gathered for a quiet reunion. Look down a column, a group, and you find elements that share a certain personality. Consider the first column on the far left, the alkali metals, excluding hydrogen, lithium, sodium, potassium, and their relatives below. They are all soft, silvery metals, easily cut, almost like firm butter. And they are eager, so eager, to connect with others. They readily give away a part of themselves, that single outer electron, to form bonds. They are the extroverts of the elemental world, always looking to react, to join, to become part of something larger. You can almost picture them reaching out, hands open. Contrast this with the column on the far right, the noble gases: helium, neon, argon, krypton, xenon, radon. Here is that sense of calm completion we spoke of earlier. Their outer shells are full, content. They have little need to react, to give or take electrons. They exist in a state of quiet self-sufficiency, like serene hermits meditating on a mountaintop, or perfectly balanced sculptures requiring no further addition. They glow gently when touched by electricity, each with its own soft color: the pale pinkish orange of neon signs, the cool lavender of argon. But mostly, they drift peacefully, aloof from the chemical hustle and bustle around them. The table places these contrasting families side by side, showing us the spectrum of chemical sociability, from the most eager to the most reserved. And between these extremes, other families reside with their own distinct characteristics. The halogens, fluorine, chlorine, bromine, iodine, sit next to the noble gases. They are just one step away from that state of perfect fullness, and so they are incredibly keen to grab that one missing piece, often reacting vigorously, forming salts. The name halogen means salt former, with the generous alkali metals from the other side of the table. It's like watching different personalities interact in a quiet, cosmic dance, choreographed by the rules embedded in the table's structure. The table doesn't just list elements, it introduces us to their families, their tendencies, their ways of being in the world. Beyond these family groupings, the table reveals gentle trends that flow across its landscape, like subtle shifts in elevation or climate across a continent. As you move from left to right across a row, the atoms generally become a little smaller, pulling their electron clouds in more tightly. As you move down a column, the atoms generally become larger, adding more layers, like nesting dolls. Reactivity also follows patterns, strongest for the metals on the far left, diminishing towards the middle, then rising again for the reactive non-metals, like the halogens, before finally falling to near zero for the noble gases. These aren't abrupt changes, but gradual transitions, like colors bleeding softly into one another in a watercolor painting. Seeing these trends laid out visually helps us understand not just individual elements, but the overarching principles that govern their behavior. It's like understanding the prevailing winds or ocean currents that shape a coastline. It gives a broader perspective, a sense of the forces at play. The periodic table has also become a kind of universal language, a Rosetta Stone for matter itself. Wherever you go in the world, a chemist or physicist will understand this chart. H means hydrogen, O means oxygen, Au means gold. It transcends cultural and linguistic barriers, providing a common framework for understanding the building blocks of everything. It's a shared map of the territory of existence, allowing scientists from vastly different backgrounds to communicate, collaborate, and build upon collective knowledge. There's a quiet comfort in this universality, a sense that despite our differences, we can agree on the fundamental components of the world we all inhabit. It connects not just elements, but people, fostering a shared understanding of our physical reality. And fundamentally, the table tells a story of increasing complexity, starting from the utmost simplicity. At the very top left sits hydrogen, H, element number 1. Just one proton in its nucleus, one electron orbiting. It's the primordial element, born in the Big Bang, the starting point for everything else. Then comes helium. He, number 2, slightly more complex, content in its fullness. Moving across the rows and down, the atomic number increases step by gentle step. 3, lithium, 4, beryllium, 5, boron, and so on. Each step represents the addition of one more proton to the nucleus, defining a new element with its own unique identity. It's like watching something grow, layer by layer, from the simplest seed to a complex organism. The table arranges the elements in this natural order of creation, reflecting the process by which heavier elements were forged in the hearts of stars from lighter ones. It mirrors that cosmic journey we contemplated earlier, showing the pathway from the simple beginnings of the universe to the rich diversity of matter we see today. So, why do we love this chart? We love it for its order, its quiet prediction of the unseen, its revelation of hidden family ties among the elements. We love it for the gentle trends it lays bare, like the contours of a peaceful landscape. We love it for being a universal language that connects seekers of knowledge across the globe. We love it because it tells the story of cosmic evolution, from the first simple atoms to the complex matter that makes up stars, planets, and ourselves. Ultimately, we love the periodic table because it helps us make sense of it all. It takes the seemingly infinite variety of substances that make up our universe: the air we breathe, the water we drink, the ground beneath our feet, the stars scattered across the night sky, the very cells within our bodies, and it shows us the underlying simplicity and order. It reveals that everything, absolutely everything, is built from a finite set of fundamental building blocks arranged according to elegant, discernible rules. It's like having the blueprint of reality spread out before us. Each element is a piece, unique but related to others in predictable ways. The table shows us how these pieces fit together, how their properties arise from their internal structure, and how they interact to form the complexity we observe. It connects the unimaginably small world of atoms with the tangible world we experience. It links the fiery hearts of distant stars with the quiet calcium in our bones. It shows us the coherence, the deep interconnectedness of all things. As you drift towards sleep, perhaps you can picture it, not just a chart on a wall, but a beautiful, peaceful puzzle of the universe. Each element finds its perfect place, contributing its unique nature to the grand, harmonious whole. The periodic table allows us to glimpse this intricate pattern, this underlying unity, assuring us that even in its vastness and complexity, the universe is a place of profound order and quiet elegance, and we are intrinsically part of that beautiful design. And so, our journey through the amazing neighborhood of the elements comes to a gentle close for tonight. Think of the periodic table, resting now, like a beautifully organized map of the tiniest building blocks that make up everything we know. Each element, from the lightest hydrogen floating like a feather, to the sturdy iron that helps build bridges, to the shiny gold treasured for so long, has its own special place, its own unique story. They aren't just names and numbers in boxes, they are the ingredients of the stars twinkling far above, the deep, quiet earth beneath us, and the gentle air you breathe in and out right now, filling your lungs softly as you rest. Feel the soft blanket around you? Its fibers are woven from long chains, built mostly from carbon, hydrogen, and oxygen atoms, all neighbors on that table we explored. The water you might have sipped before bed, so cool and clear, is simply hydrogen and oxygen holding hands tightly, working together perfectly. Even you, resting here so peacefully, are a wonderful collection of these very elements. Calcium is quietly making your bones strong while you sleep, helping you grow. Iron atoms, nestled within your blood, are carrying life-giving oxygen on tiny, silent journeys through your body, with every gentle breath you take, reaching every part of you without a sound. It's like a quiet, invisible dance happening all the time, everywhere, even as the world outside grows still. The table itself shows us a beautiful pattern, a quiet order hidden within the universe. Remember how elements in the same column often act like family members, sharing similar ways of being, like quiet cousins who understand each other. The noble gases, happy and content on their own, resting peacefully on the far right side, needing nothing more. The alkali metals, always eager to connect and share, over on the left. It's a gentle reminder that even in the vastness of the cosmos, there's a comforting structure, a predictable rhythm, like a soft, steady heartbeat. There's still so much more to understand. Of course, more quiet wonders tucked away in the corners of the universe, perhaps even new elements waiting patiently to be discovered someday far in the future. But that's a story for another time. another peaceful evening. For now, just like the elements have settled into their perfect places on the table, organized and calm, it's time for you to settle into your cozy place in bed. Let your thoughts drift, soft and light, like helium rising slowly towards the ceiling. Feel the quiet peace of the night wrapping around you, knowing that you and everything around you, the bed, the air, the distant moon, are part of this grand elemental tapestry woven together long, long ago. The universe is humming its quiet, ancient song, made of stardust and atoms, and it's time now to rest. Sleep well, little explorer. The elements will be waiting, quiet and patient in their places, for our next adventure whenever you're ready. Sweet dreams.